So this is our second day of the introduction to vectors, but basically we're going to concentrate on the bearings. This worksheet, I think the entire worksheet is your assignment technically, but these are pretty nasty, and I wasn't real excited about my last recording. I don't think I did a stellar job. So remember, we do have a book assignment, so keep that in mind. But on worksheet 2, this is part of that assignment, and these are all questions, all the notes you need are from the first worksheet. However, remember when we're doing bearings, we offered you the two options. The tip to tail method, which is the one where you end up doing law of sines and law of cosines in your math. And then the other method is the adding the components method, where you find, you put I don't know how they described it, but you put the two vectors together and you add them together by creating a new vector by adding the components. So the more I do these questions, the more I just don't care how you do them. But I noticed that if the question specifically asked me for components or rectangular components or something like that, or what do they call it? Yeah, they call them rectangular components in your book. I'm going to use the method where I find the magnitude times cosine theta and then magnitude times sine theta. It just makes sense. If they're going to ask for components, that's the method I'm going to use. So I think for some of these questions, I'm going to skip over them because they are your homework, and I'm not worried about 1 or 2. But number 3, my key is a hot mess because I tried to fit in both techniques. Get rid of that. Both techniques on the key. So how about, I kind of wish I already taught this lesson because then I would know from you guys which technique you want. But I know a lot of you are in physics, and I think you use the law of cosines method a lot in physics. So how about I do this question the law of cosines way? And then the next question we talk about the components. Technically, we can use whatever method you want because you can still find the components using the other technique. It's a bit of a roundabout, that's all. All right, so if you draw like I draw, you're going to probably want to do your work on another sheet of paper because you're going to want a larger drawing just so you can fit in all of the angles and parallel vectors and all that good stuff. All right, so this is using the tip to tail method. So Carolyn walks 45 degrees north of west, 1,000 feet. Okay, so north of west. Oh man, I think I already screwed up on my key there. Oh well. Alright. Gosh, be golly, timeout. Alright, I know what I gotta do. I'm gonna shuffle my axes over. Oh, jeez. Over a little bit here. So she is walking north of west. So here's west, so 45 degrees north would be like here. And that's 1,000 feet. Okay. And then I should also include the angles. So this is a 45-degree angle here, but that means this is also a 45-degree angle. I'm going to keep that there. Now, earlier on the lesson, I was drawing the vector like around the same origin point. But remember, like these are vectors, so like the new vector can join up with it at any point. So the tip to tail method basically is saying, go to the end of your first vector, create like a new origin that's parallel vectors to it, and then create your new vector. So then she's going to what? She walks 200 feet due north. Oh, that's exciting. And I didn't draw this to scale. What's new, right? This is 200 feet. So using the tip to tail method, that would be your new vector or your resulting vector. And since I can't draw, I can't fit anything on here, this is what we need to find. And then we also need to find the bearing at some point. So that angle is what we need to know. Well, that angle is actually pretty easy for us to find if I can remember some geometry basically. So 45-degree angle, if this is 45 degrees, that means that this over here and this over here is also 45 degrees. So right here in this angle, we have a 90-degree angle plus a 45-degree angle. So that angle right there is 135 degrees. See what I mean by wanting a bigger picture? Because I can't fit anything on here. So now if I was using my physics technique or the tip to tail technique, I would use law of cosines. And to find x, I'd set up x squared equals 1,000 squared plus 200 squared minus 2 times 1,000 times 200 times the cosine of, we just found that to be 135. And then don't forget, you got to square root this number. So I usually just type this in one step in my calculator if I'm using this method. And using this method, I get a magnitude, a resulting magnitude of 1150.1 meters, or feet. Wait a Mr. Dredge visitor. All right, we're back. So feet. Now, what I need to figure out next, because I think they also want the quadrant, north of west quadrant bearing. So I need to figure out the angle. I should probably color it something else. From here to here. All the way to the blue line. Well, I know that this part was 45 degrees, so if I could figure out this teeny tiny angle right here, call it A, then I can add it to 45. So now we'd set up law of sines. And I'd set up sine of that 135. Across from the 135 I now know is 1150.1. And then to find this little green angle here, he's across from the 200. So sine of A over 200. So after I multiply, divide, and then apply the inverse sine, I find out that that little green angle A is something little, 7.1. So the bearing itself, if I add that 45 degrees to it, gives me 52.1 degrees, and that would be from here to here. So that would be our north of west bearing, and we'd label it such when we write out our answer. So that was the physics technique. What if for fun I went back and I did that same question using the other technique? Maybe that's what I'll do, and that way you get a choice. So if you're not interested in the components technique, then skip ahead, but I will tell you, you probably want to use the components technique at some point. All right. Oh, gosh. Try this again. You know, I really, forget it. I really should learn to just do a better job of having axes ready for me to go. All right, so same starting vector, 45 north of west. 1,000. And then remember, this was a 45-degree angle here. But when I use the components technique, what I really need is the angle from the positive horizontal axis, like a standard position angle, if you want to remember it that way. So 90 plus 45 would be 135. That would be the angle we're going to be using here. So for the components of the original vector for Carolyn, that would be 1,000 times the cosine of 135, comma, 1,000 times the sine of 135. All right, I'll leave that alone for a minute. Because all my math I do it on like one step on my calculator, basically. Or two steps, I guess, because you got to find the two components separately. So her other vector is 45 degree, due north, right? Due north for 200 feet. So like this. So that's, I can't write on here because I don't have any room, but a magnitude of 200. And the angle from standard position would be 90 degrees. So some of you might be thinking like, well, isn't it kind of stupid to write like the cosine of 90 because that's 0, so this whole thing is 0. Yeah, but you know, whatever. At least you know where these numbers are coming from. I'm glad if you recognize that's what it was. Same thing with sine of 90. You know that's a 1, but whatever. So here's the idea. To find the resultant vector, you're going to add these two together. And I think I did that at some point. So I typed them in degree mode, all that good stuff. My resulting vector is negative 7 point, no, it's not. Negative 707.1, comma, 907.1. So in order to find the magnitude or the resulting vector's length, you do Pythagorean theorem. Because here's what's happening, guys. If I had space to do this, I sure would. But on that same coordinate plane, which I can't fit any more work on, negative 7.07, 9.07, this is the resulting vector. So what you're doing is you're doing Pythagorean theorem on this little triangle. Okay, so I leave the negative off because it's going to go away anyways. It's negligible because you're going to square. That's a 0.1 right there. When I type this in, my magnitude comes out really close to 1150 feet, which remember on our other method we got 1150.1. So because of rounding up here, there's a little bit of truncation issue, and we're a tenth off from the other answer. So I don't know who's a better answer at this point because I didn't keep a lot of decimals anywhere in my work. All right, so there's our magnitude. And then what I would do next, because remember they want the angle with north of west, so call that theta and just find it. So remember trig, we can use inverse tangent. So I'm going to set up the inverse tan, because this was, what was this, 907.1, and this is negative 707. And I know it sounds stupid to call it negative, but it is important because of the coordinate plane issue. So inverse tan of 907.1 divided by negative 707.1. And I find theta to be, now on my calculator it comes out to negative 52.1. So my calculator is giving me, this angle right here. But remember, this angle is going to be the same, oh hello, kickin' brain, reference angle to this theta angle over here. So this guy, the amount of space between the horizontal and the resulting vector is 52.1 degrees, which is the same answer that we got on the other method, so that worked out. So again, you do not have to complete both techniques, just pick one. The construction questions, it's actually quite easy, and it does mention that they want the horizontal and vertical components, so I might suggest that you use the component method. Pulling a force of 60 newtons at an angle of 42 with the horizontal, excuse me. So they want me to draw a diagram here. 42 with the horizontal looks something like this. This is 42 degree angle, and then a force of 60 newtons. So they just want you to draw the diagram there, and then if you continue on and find the horizontal and vertical components, I don't mind if you write it in that vector component. It looks like an ordered pair form, or if you just want to label them separately, that's fine too. But the important thing is that you know which type. So magnitude times the cosine of your positive x-axis angle, and then magnitude times the sine. And they don't even want the magnitude of the resultant vector, or there's only one vector going on, ignore me. Alright. Yeah, I'm silly. I did some weird work on my key, what's new? Alright, anyways, this comes out to 44.6 newtons on a horizontal force, and then 40.1 on the vertical force. And that says newtons. So that was a pretty easy question, and clearly there's no technique to use because there's only one vector. Hello, Abruzzo. Bring your brain out. It's Monday. Alright, an airplane is flying with an airspeed of 500 miles per... Oh, you know what? I'm going to skip this one because it's actually really easy because of the due north thing. It really just turns into a really basic trig question. But let's take a look at this one. Now, again, it asks about the horizontal and vertical components, so I might suggest that you use the component technique, because this time we do have two competing vectors. Plus, the way the diagram's set up, it kind of works out perfectly for that. They want the sum of the horizontal components. So, we have to be careful with this angle right here. If we're using the component formula, this angle is a negative 20 degrees, so keep that in mind. So the sum of the two horizontal components and the sum of the vertical components. So basically they're asking for the resultant vector. Here's what I would do. Gigantic space here, right? The horizontal parts for each vector, for the first vector, let's call it that 2,000. So 2,000 times the cosine of positive 20 degrees, and then you're going to add to that the other vector's horizontal component, which is 1,500 times the cosine of negative 20. Oops, I didn't anticipate how much work I was going to have here. Let's keep going. And then for the vertical components, 2,000 times the sine of 20 degrees plus 1,500 times the sine of, remember that's negative 20 degrees. So typing this in my calculator and then typing this in my calculator separately, whoops, hello, we get, yuck, 3288.9 newtons. I don't know if it's appropriate to label within the vector components, but I am. I'm a rebel like that. And then 171.0 newtons. That looks really weird. I don't know why. And then the resulting force is us finding the magnitude. So that's the square root of 3288.9 squared plus 171.0, whatever, squared, results in approximately 3293.3 newtons. That's what we want, is the resulting force. And then there's a part C question. It actually isn't on your homework, but it talks about changing the angle. We'll come to that. Alright, orienteering question on the back, I think, is pretty basic. I'll let you try that one. And if I could suggest, from here on out, I think it would be best to use the component of the vector addition. So instead of using your physics technique, I think the book questions are really set up nicely for component form. That's my suggestion. I'm gonna stop doing your homework for you there. And best of luck to you. Hopefully my answer key is legible.